Hey, I'm Chi. I'm the H2H8 Guardian for Quantum Physics and Material Science, and today I will be telling you more about dualities and quantum gravity. So let me start with a bit of motivation. My favorite way to think about the story of physics is to think about the story of how dualities was discovered. The story begins when Newton realizes that the force that causes an apple to fall to the ground is dual or identical to the force that causes the Earth to go around the sun. And that sort of opens the floodgates for people to discover new dualities or relationships between seemingly unrelated things, and that is currently our best guess as to how a theory of quantum gravity, more commonly known as the theory of everything, really operates. So we believe that there is a duality between a gravitational theory and a non-gravitational theory, and that duality sort of sits at the heart of how we understand quantum gravity. For instance, there's a duality between a kind of minimal string theory, which makes it dual to matrix integrals, and another classic example of this duality is the duality between the ADS spacetime and a conformal field theorem de boundary known as the ADS-CFT correspondence. And the big open question is, what is the non-gravitational dual for a space-time theory potentially with matter? And if we answer that question, we will have our theory of everything. Today I'm going to be looking at the second line of this duality, which is the duality between minimal string theory and matrix integrals, and we will be matching certain quantities across the duality, and hopefully we learn more about the space-time theory by thinking more about these dualities. So that brings me to the technical title of my talk, which is Matching Instantons in Matrix Integrals and String Theory. This is based on a paper with Dan Stefan and Raghu Mahajan at Stanford, and also Professor Ashok Sen in India, who's one of the world leading string theorists. Okay, so in terms of overview, I'm going to first introduce what instantons are. Then we will talk about these instantons in the context of matrix integrals, and finally I will talk about the instantons in context of string theory. So let me begin by telling you what saddle point approximation is. The basic idea is that given an integral that sort of looks like e to the minus nx f of x, the graph is sketched in the thick blue line, you can approximate it using that sort of dashed blue line answer, especially in the limit that n becomes large. And that is the key idea behind the saddle point approximation, that the big blue integral, especially in the n goes to infinity limit, looks like the dashed answer. The point at which the contribution comes from dominantly is the maxima of this curve, and clearly we believe that it would satisfy something called the saddle point equation, which is that the first derivative at the saddle point vanishes. You can cast almost all of your physics theories into this form, and any sort of equation of motion coming from, say, Newtonian mechanics or electromagnetism or Einstein's theory of general relativity can all be cast into a saddle point equation for the relevant theory. So this is sort of the most important equation that can describe a lot of physics in a lot of contexts. What an instanton is it's also a solution to the saddle point equation, but it's not the dominant solution, it's a subdominant solution or a subleading solution that gives you non-perturbative corrections to the integral. So with that sort of introduction to instantons, let's see if we can use these techniques to compute things in matrix integrals and match them to string theory. So matrix integral, as the name says, is some sort of integral over matrices, which we call the partition function, and after recasting it, you can write it as an integral over the eigenvalues of the matrix. To make our lives a little bit easier, let us integrate over all but one eigenvalues, and we end up with something that's just an integral over that remaining eigenvalue lambda, and some other terms that come from doing all of the complicated integrals that I will sort of call the e to the minus v effective, where v effective is the effective potential. Similar to the saddle point equation we saw earlier, the saddle point equation now is just that the first derivative of the effective potential vanishes at lambda. So here is what an effective potential typically looks like. So for lambda bigger than 0, you have this very flat region. Any point in that region satisfies the saddle point equation because the derivative of V effective vanishes, and that is what we think of as the allowed region. So the contributions that come from there are the dominant contributions. On the left of the graph, you can see a point lambda star, which is also where V effective vanishes because it's a maximum of V effective, but that will give us a subdominant contribution, and that's what the instanton is going to correspond to in the matrix model. So work in this context was done by a couple of people, including Ishibashi, Kuroki, and Yamaguchi, and in the context of a special model that we will be working with called the 2, P model, this is what that integral at lambda star gives you. The one thing that I want to point attention to is the fact that the value at lambda star, which is e to the minus t, goes like e to the minus 1 over g string. G string is what we identify as a coupling constant, and a lot of our understanding of physics comes from expanding things in a Taylor series about the coupling constant being 0. So this is a e to the minus 1 over g string effect, which is something that perturbation series cannot capture. So if you've taken a calculus course, at some point you might have noticed that the function e to the minus 1 over x doesn't have a Taylor series expansion. All of its derivatives vanish, and there is no good way to characterize it using a Taylor series approximation. And that's why we call these contributions non-perturbative, because they cannot be captured by a perturbative Taylor series. Okay, so that was the matrix model calculation. Let's now dive into the string theory calculation. In the string theory side, the perturbative answer is given by something called a genus expansion. So a genus expansion you should think of as a topological expansion, where I sum over the different sort of two-dimensional surfaces that I can have. So the leading contribution is the sphere, you have the torus, which you should imagine as a donut, and you have a double torus, and so on and so forth. These are together making up the perturbative contributions, but we are interested in the non-perturbative answer, and that contribution comes from something called the ZZ instanton. The ZZ instanton typically arises when you first consider these objects called branes. What these branes are there locations where your string, the closed string, can end or terminate. So in this figure, you can see that the white represents a closed string that sort of starts at one of those circles, lives for some time, and then ends at the other circle. And given a ZZ brane, you can either have 0 closed string cylinders, 1 closed string cylinder, 2, or more and more, and you can sum of all of this as an exponential of the cylinder. So you basically get a closed string sort of cylinder piece exponentiated multiplied by the purely ZZ brane piece. Now the ZZ brane piece goes like e to the minus t, and that is why this is a non-perturbative contribution. And what we are now interested in doing is calculating that exponential of the cylinder and matching it across to the matrix integral answer. So we express the cylinder starting with the closed string channels. You can think of this closed string that travels and ends on the other cap. You can reinterpret this as an open string channel answer, where you have an open string that sort of propagates in time and after some time sort of re-merges with itself. So you can see the cylinder in a different way, and you put some appropriate measure of integration and do the integral for the open string time that runs from 0 to infinity. After you do the computation there, this is what the integral looks like, and if you stare at it for a couple of minutes, you will realize that the integral, as I have written here, blows up, and it blows up in the t goes to infinity limit, which is the large distance or large time limit, and this is what we call an infrared divergence, because it's diverging in the large distance limit. These are typical divergences that you expect for theories that have either massless states or negative mass states, and we know how to cure these divergences. For that, we have to call in this tool called string field theory. So the next goal of my talk is going to be curing these divergences using string field theory. So to regulate the divergence, we write this answer for the exponential of the cylinder as this complicated looking expression, and this is only the divergent piece. So you have two positive terms with different exponentials and a negative term with a third exponential. If b1, b2, and f are all positive, we know what the answer is. It's just f over square root b1, b2. You can do the integral out. And you can recast that answer as a bunch of bosonic or real integrals and a fermionic integral. So the square root b1, b2 comes from the bosonic piece, and the f comes from the fermionic piece. Once we've converted it into these integral forms, we can resubstitute our values for b1 and b2, which were -1 and 1, and we can also put in f equals 0 and then do the computation once we have this new picture. So let me start with the bosonic integral. The second answer is pretty nice looking. It's just a normal Gaussian. You can do the integral. The first answer has an issue. It's sort of a Gaussian with the wrong sign. To fix that, what we do is we rotate the contour of integration in the complex plane, and instead of integrating from -infinity to +infinity, we rotate the contour and integrate it from -I∞, which is some point in the complex plane, to 0. That integral after the rotation is finite, and because of that contour, we get a I/2 as the answer. So that's the bosonic piece. The main subtlety is associated with the fermionic piece, and the fermionic integral is ill-defined because a central gauge choice in string theory called the Siegel gauge choice completely breaks down in this case. To regulate this, we switch to fields in a different gauge called the physical gauge. These, for people who understand technical details, correspond to the fields that have ghost number 1, and once you sort of go to this physical gauge condition and divide by the volume of the gauge group, you get a perfectly finite answer that looks like square root pi over square root 8 pi squared square root t. Okay, so now that gives us all the different pieces that we were interested in, and we can combine them and match that to the string field, to the matrix theory calculation. So you have the ZZ-brane piece, you have the bosonic piece, you have the fermionic piece, and finally the finite piece, which comes from all the other terms in the integral. This answer that we get after doing all of the proper regulations using string field theory matches exactly with the matrix model calculation, and that was what we were expecting. So in conclusion, we computed instanton contributions in minimal string theory by using string field theory, and then we were able to match this contribution to the results from matrix integrals. Thank you for your attention.